that is Schmitt trigger. Okay, so let me first give you an introduction about the clampers. My screen is visible. Okay. So those who have not completed this clampers experiment, they may also perform it today. Okay, so what are the clampers? Clampers are actually the circuits which are used to shift our output signal to a defined DC value. Okay, and we have positive means either the positive peak or the negative peak is shifted to a defined DC value. So that is why we have two types of clampers. One is negative and one is positive. And since this shifting of entire signal either to upwards or downwards happens, so that is why this clamper circuits are also known as level shifters. Okay, the whole output signal is being shifted to the other desired value level. Okay, so how does this happen? It actually depends on the charging and discharging of capacitor, which we connect along with a diode in parallel with the diode. Okay, so in one half cycle, the capacitor charges, and in the other half cycle, the capacitor starts discharging. Okay, so we also get the output as well as that the voltage which is provided by the capacitor, that is added up with the output signal. That is why we get a shifted form of output. Okay, but two things we should be careful about these clamper circuits is that the capacitor must not be chosen such that the conduction of the diode, during the conduction of diode, capacitor must be sufficient to charge quickly, and it should not discharge very means drastically, right? Okay, so first this circuit is for a negative clamper, sorry. So what we do in this, when we give positive half cycle, during the positive half cycle, what happens? This capacitor C starts charging, and the diode is in forward, means forward bias. So diode will act as a short circuit. So what will be the output? In at the output, we will get nothing. Okay. Now during the negative half cycle, what happens? During negative half cycle, the this diode is reverse bias, so it will act as a open circuit. Okay, so whatever input we are giving, we will get that same input at the output, plus the capacitor has now charged completely to up till the this suppose the peak of input signal, positive peak is suppose capital V. Okay, and the negative peak is also means positive is suppose plus V, then negative will be minus V. Okay, so what will happen? Where, during the negative half cycle, the output which we will get will be what? Will be the input which we are applying, that is the positive plus V, sorry, negative V, and the voltage which already has been developed across this capacitor due to the charging of capacitor. Okay, so the output which we will get will be equals to the twice of V. Okay, so that is why you can see in the output we are getting a complete waveform, but this is shifted to the negative side. Okay, so now what will be the peak of this output voltage? The peak will be twice of V. Okay, so you can see the voltage has, sorry, this waveform has been shifted towards the negative direction. That is why this circuit is known as negative clamper. Okay, Now this is the negative clamper with some positive reference voltage. Okay. So now here what happens during the positive half cycle, our diode is forward bias, so it acts as a short circuit. But during the positive half cycle also we will get some output. Okay. So what is that output? That will be equals to VR. VR voltage which we are applying with the along with the diode. Okay, so that VR we will get in the positive half cycle. Then during the negative half cycle, what will happen? The diode will be open circuited, right? So what will be this output which we will get? That will be again that will be equals to twice of V. But what will happen? This VR will be minus from that twice V. That is why we are getting this output waveform is shifted towards negative direction, but some VR value we are getting for the positive half also, means in the positive means in the first quadrant. Okay, due to this presence of this VR. Okay, because this is getting subtracted from the twice of V. Okay. Now this is the positive clamper. So this operation is same, but this time our output will be shifted in the positive direction. Okay. Again, this is positive clamper with positive VR. So again, since we have applied the positive clamper and also the positive VR, so the shifting of this waveform will be twice of V plus VR. Okay, so both of these this output will be added up. Okay, positive clamper with positive VR. If we would have applied the negative VR here, then there will be some part of this waveform will be in the negative half. Okay, like this. We have applied positive, we have made positive clamper with negative VR. Okay, so for that we are getting if some part VR portion we are getting in the negative half. Okay, so that is all about the clampers, and now we shall start with the experiment number 6, that is a schemic trigger. Okay. So that clamper experiment, have you all done, or few people are there who have not done still? Clamper experiment, experiment number 5. All of you have completed it. Please respond. Is there anyone who has not completed experiment number 5? All of you have done, that means, because there are few people who have not submitted your copies still. So that
No,
is why
ma'am,
I'm
not
asking.
not done, ma'am.
Not done, right? Anybody else who has not done? Okay, so today, because last time very few people have shown me experiment number 5. So today you have to show me both the experiments, experiment number 5 as well as experiment number 6. Okay, so, okay, let's first discuss this circuit, then we'll. Okay, so schemic trigger, what is a schemic trigger? It actually gives two level triggering, means there are two threshold voltage levels at which our output can be triggered. Okay, for the rising and falling edges we have different voltage threshold voltage points. Okay, levels. So this hysteresis kind of loop we can see. Okay, for example, we have VCE saturation, that is the this lower point of triggering, and then VCC is the uppermost. Okay. So for the input signal, we are getting 2 points. This is LTP and UTP, right? LTP and UTP. Both these points we are getting for the two transistors which we use.
Excuse me, ma'am. Your PPT is
Yes,
not visible, ma'am.
PPT is not visible. Wait a minute.
Yes, ma'am, it's visible.
Now, okay. Now, so this kind of hysteresis loop you can obtain because this LTP and UTP points are those points at which the two transistors which we use in our circuit they actually are conducting one at a time. Okay. So when one transistor conducts, then we get LTP points. When the other gets start conducting, we get this UTP point, upper tripping point and the lower tripping point. Okay. So, sorry, upper trigger point and lower trigger point. Okay, so that is why we get this hysteresis kind of loop. Okay, so uh, from here you can see we have two stable states, VC saturation and VCC. Okay, so we have two stable states. That is why this skimmed trigger is known as a bistable multivibrator. Okay, so bistable multivibrators are a class of circuits or yeah, circuits which we use in our devices. So skimmed trigger is a kind of bistable multivibrator. Okay, and its output actually remains in either of the two stable states. Bistable means we have two stable states. So until and unless we apply some input voltage or we do something to change its state, the output will not change its state automatically. Okay, so in order to change the state of our circuit, we have to give some trigger. Okay, so okay, yeah, for the output to change from one stable state to other, the input signal must change appropriately. Okay, so hence it may be used as a level detecting circuit as well. Okay, because we are having two levels, right? I told you this is VC saturation and VCC. We have two levels, so it can be also used as the level detecting circuit. How? I will tell you in further slides. Now, this bistable operation of schema trigger requires an amplifier with positive feedback. Okay, so in this schema trigger, what we do, we provide a mechanism such that our output means we do not have to manually we don't want to change the input. Okay, so we apply some positive feedback kind of thing so that the output gets triggered from one stable state to the other stable state. Okay, so what is a positive feedback? Positive feedback means we give a loop kind of thing is created, and in that feedback loop the gain is greater than 1. Okay, so this triggering of states from one state to another state is actually obtained by this positive feedback loop. Okay, and this schema trigger is also known as a regenerative comparator, right? So this is the figure which you might also have used in your experiment. You will be using this. Okay, so Q1 and Q2 are the two transistors. Okay, and the output of Q1, that is the collector terminal, is coupled to this Q2, the base of this Q2, right? So means output of one transistor is coupled to the input of the other transistor. Okay, so if the output of Q1 goes low, the Q2 will, the base of Q2 will also go low. And if the base of Q2 goes low, then what will happen? Q2 will stop conducting, right? That this is the kind of loop we have created, the positive feedback loop. Okay. So, and the emitter of both the transistors have been tied together with RE resistor, all right. And the C1 is a coupling capacitance we have applied here. Okay, RC1 and RC2 are collector resistances for both Q1 and Q2 respectively. Okay, and we are giving the input at the Q1 only. Okay, so now what happens when we apply some power? The Okay, when we apply some V in voltage, so you can see this RC1, R1 and R2. These three resistors, RC1, R1 and R2, they form a voltage divider kind of circuit. Okay, so this VCC which we have applied, this VCC will get divided across this RC1, R1 and R2. Okay, so we by voltage division rule we can easily find out the voltage at the base of this Q2. Okay, so when some we provide some voltage, we what will happen? This Q2 will start conducting. Means as soon as we provide some VCC when we apply, this VCC will get divided between RC1, R1 and R2. So some voltage will be there across this R2. Okay. So across this R2, we fix these RC1, R1 and R2 such that our Q2 starts conducting. Okay. So when this Q2 starts conducting, what will happen to the output? What will happen to the output? The current will flow through the RE resistor and there will be some voltage drop across it. Okay, so the this if Q2 is conducting, the output will be what? Zero, because whole of the current will go through this transistor and it will go to the ground. So we will not get anything at the output. Okay. So now there will be some drop at this RE resistance. Okay. So because of this drop, what will happen? This Q1 will be driven into cutoff mode, right? There will be some drop at this Q1 and it will be driven into cutoff region. This all is happening when we have not applied this V in voltage still. Okay, Q2 is conducting and Q1 is cut off. Now, when some V in is applied, Q1 starts conducting and the capacitance voltage at this Q1 will start dropping. Okay, so when this voltage starts dropping, what will happen? This Q2, base of this Q2 will also start dropping voltage at the base, and then what will happen? This Q2 will stop conducting and Q1 will start conducting. Okay, so this is a kind of loop we have created here, positive feedback loop. Okay, so the two transistors, when Q2 starts conducting, that is known as the upper trigger level, and when this Q2 starts conducting, that is known as the lower trigger level. Okay, so these two kinds of triggering is has been made here, and this cycle actually repeats as the input AC signal repeats its cycle. Means for the positive half, when the cycle when the input is positive, okay, then our Q1 will be conducting. Okay, and when our input starts going towards the negative half cycle, then for negative half cycle Q1 will again go to cutoff mode and then Q2 will start conducting. Okay, so according to this V in signal, for positive V in, Q1 will conduct, and for negative V in, Q2 will conduct. So that is how we are getting a this hysteresis loop kind of thing we will get. Okay. So this amount of hysteresis can be changed by changing this RC1, RC2 and RE values. Okay. And RE can be used to increase the upper threshold voltage as well. Okay. So this kind of output you will get. The upper waveform is the input waveform. Okay. And you can see the upper trigger point and the lower trigger point, right? As the input reaches this upper trigger point, the transistor Q2 will be off and Q1 will start conducting. Okay. And you can see we have taken the output from the collector of both the transistors, from the collector terminal of Q1 and from the collector terminal of Q2. And you can see when Q1 is on, Q2 is off, and when Q2 is off, Q1 will be on. Okay, so this kind of waveform you will be getting according to the trigger levels. Fine. So this now the applications of this schemic trigger, they are used in signal conditioning applications. Like main application is the removal of noise from the signals in digital circuits. Then they are used for squaring circuits. Also in the amplitude comparator or level detector, I have already told they are used as the level detectors. Then they are used as flip-flop circuits as well. Then they are used for reshaping of the worn out pulses. Like you can see, we are getting the square pulse at the output. Okay. So if your pulses are worn out, then they are this schemic trigger can be used as the wave shaping circuit. Then they are used to implement relaxation oscillator in function generators and switching power supplies. Okay. So that is all about the schemic triggers, and I think now you should start doing your experiment. So this experiment 6 is clear to all of you.
Yes, ma'am.
Okay. So please start doing your experiment 6, and those who have not done this experiment 5, they also perform experiment number 5, and today you have to show me both the experiments, 5 as well as 6. And from Wednesday, uh, I will be dividing you all in two batches. Okay. So from coming Wednesday, because from tomorrow your offline classes will be starting. So have you all returned to campus, or you are planning to return in 1 or 2 days?
Ma'am, actually, for
Okay.
now we have sharing rooms, ma'am. So we are not planning now, ma'am, because of sharing rooms.
You are sharing rooms. Where?
No, 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 not like
In,
that. We were when we joined the college, we were in first year, ma'am. Then we came here.
uh-huh.
So we are having a single room for two people in the hostel, ma'am. So that's why we are
Okay.
not thinking to come, ma'am.
Okay. Okay. So all of you are not coming, or few of you are already here? What about others?
Ma'am, is it visible, ma'am?
Yes, it is.
Ma'am, this is the circuit, ma'am, and I took 7.07 as my RMS, ma'am, with 1000 hertz
Hmm.
as my frequency.
Okay.
Ma'am, this is the waveform I'm getting, ma'am. Yes, ma'am.
All right.
Ma'am, here are the points, ma'am. The thresholds, upper, upper and lower threshold, ma'am.
Okay. Okay, fine. So you can see this is not a perfectly square wave, right?
Yes,
For
ma'am.
this negative half, the time period is larger
Yes, ma'am.
than
A
for
spherical wave,
positive.
ma'am.
Okay. Yeah.
Yes.
So this you are measuring at the collector of which transistor?
Ma'am, collector of second transistor, ma'am, here. Collector of
Q2. Okay.
Q2, ma'am.
Okay. So you can also plot it for Q1, collector of Q1.
Yes, ma'am, I'll try it now.
Okay. So you will get just opposite of what you are getting in this. It is kind of distorted because there might be some wiring issue.
Ma'am, actually I kept it before the register, ma'am. I'll try it after register.
Okay. Yes, yes. No, no, collector terminal is after the register only, na?
Yes, ma'am, here it is.
Hmm.
Ma'am, here this is the point where I kept the attachment, ma'am. The oscilloscope.
No, no, no. You have to put it just next to the collector terminal of the transistor.
Ma'am, here, ma'am.
Yes.
Yes, ma'am. This I kept, ma'am, last time, but we are getting the half square and half sine waveform.
That might be due to some other issues. No problem, no problem.
Ma'am, I guess because of this RC here we are keeping here, no, ma'am. Because of that here it's happening. When here we are keeping it's passing through RC and coming like that. Ma'am, can I stop sharing the screen?
Actually, yes, 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 please.
Sorry, this point is where the upper threshold point, where the input voltage is greater than the threshold value of Qn, and Q2 goes off in this situation uh, because of the feedback circuit, because of the regenerative action. And this is where this is the LTP, lower threshold point, where Vn again becomes lower than here. Vn again becomes lower than the threshold values. So uh, I guess Q1, this goes off. This goes off. This is the output that I'm getting.
Okay. Okay, okay, fine.
Thank you, ma'am.
Sarthak, what is your roll number?
Ma'am, 202.
My screen visible.
Hmm. Yes.
Ma'am, I have taken the trigger point to be 2 volts, but I don't know if my graph is correct or not because VSAT is around 2 volts for me here.
Hmm.
Uh, I don't know if it is correct because V
Hmm.
saturation is usually like in 0.2 volts. So, ma'am, the red one is the input,
Hmm.
blue is from the collector 2, and green is from the collector 1.
Okay.
And the trigger point is at 2
No,
volts.
output is fine, but why it is showing shifted to
Yes, ma'am. Uh,
why it is shifted upwards?
Ma'am, I have taken the lower triggering point to be 2 volts. So when I have adjusted my
Okay.
resistance according to
Okay.
this,
Okay. Mm-hmm.
then the graph was shifted upwards.
Okay. Fine.
Yes, ma'am.
So you have shown me all other experiments.
Yes, ma'am. I have already shown the previous 5 experiments. My roll number is 212, ma'am.
Yes. Okay. Okay. Fine, Prasad. Next is Shashwat.
Okay.
Yes, ma'am. Should I present, ma'am?
Yes.
Uh, is my screen visible, ma'am?
Yes, it is.
Yes, ma'am. Ma'am, so this is the clamper circuit. All 6 clamping circuits I've done with reference voltage, with 0 voltage, and with negative reference voltage too, ma'am. So these are
Fine.
the outputs. Ma'am, this is for negative clamping circuit with no reference voltage.
Okay.
This is for positive clamping circuit with negative reference voltage. Here I've connected 3 volts in the opposite direction for negative
Okay.
negative reference. This is, ma'am, positive clamping with 0 voltage. So this is, ma'am, 1 minute. Yes, ma'am, this is negative clamping with negative reference voltage. This is positive clamping with positive reference voltage, 3 volt only, just connected in opposite direction, just like here I did in the negative reference voltage, ma'am.
Mm-hmm.
Positive
Okay.
terminal is this side and negative down. And this is, ma'am, negative clamping circuit with negative reference voltage. So this, ma'am, this is experiment 5. And in experiment 6, using transistor, I created the Schmidt trigger. I haven't studied it yet, so I might not able to explain, ma'am, anything.
It's okay. So maybe.
I just know the graph and not much. So the graph was coming like this, ma'am, but to be honest, I don't have much idea.
Okay, here you are showing the output of one of the collector, and I think it is the output of collector 2, means collector of Q2,
Uh,
right? You are taking the output from collector
Ma'am,
of,
here
yes,
there are 2 transistors, Q3 and Q4. I think it is the output of
Q4,
this.
yes, Q4
Q4,
you are
yes, ma'am.
taking, right?
Yes, ma'am. Yes,
Q4
ma'am.
you are taking.
Yes, ma'am.
Okay, fine.
So,
So
ma'am,
what is happening here? You will be having two tripping points here,
yes, ma'am.
trigger points, you can say, right? So the trigger point means where your one transistor is starting conducting and the other is stopping. And the second trigger point you will get when
The
the
other is
first one
conducting
gets,
and this is
yes,
stopping.
and first
Yes,
one
ma'am.
is not conducting.
Yes, ma'am. Yes, ma'am.
Okay, so
Yes,
if you will take this output from the collector of first means Q3, so you will see the difference. You will see when this Q4 is on, your Q3 will be off.
yes, ma'am.
Okay, and the tripping points you can see from here, the this lines where they are crossing the input signal, the
Ma'am,
output.
which line, ma'am?
The output where this green and red are meeting points, the two meeting points, they are the
Yes,
is the rising edge and falling edge of the square wave.
yes, ma'am.
They are the two tripping points. Means
Yes, ma'am.
at this point, the transistor is going on and the falling edge means the transistor is going off.
Yes,
When
ma'am.
this transistor is going off, the other will be
On.
starting conducting.
Yes,
Okay,
ma'am.
other will go to on state. Okay, okay, fine. So Shashwat, your roll number is 0038, right?
1038. Yes, ma'am.
Fine.
Should I stop presenting?
Yes, yes. Next is Ashish.
Yes, ma'am. Ma'am, is it visible?
Yes.
Yes, ma'am. Ma'am, first I'm showing the clipper circuits.
Hmm.
Ma'am, this is a negative clipper with zero reference. Then this is positive clipper with zero reference.
Hmm.
Ma'am, this is also positive clipper with zero reference. This is shunt clipper, and this is negative clipper with zero reference. The shunt one.
Okay.
Ma'am, it is positive clipper with positive reference. Ma'am, this is negative clipper with positive reference.
Hmm.
And negative clipper with positive reference. And this is also negative clipper with positive reference.
And this
Ma'am,
one is in
ma'am, double-ended clipper.
next. This is number.
Ma'am, this is negative clamping with zero reference.
Hmm.
This is positive clamping with zero reference. This is positive clamping with positive reference. This is positive clamping with negative reference.
Hmm.
This is negative clamping with positive reference.
We have understood all the working why and how the circuit is acting as a slipper and how it is acting as a damper.
Ma'am, can you repeat?
Have you understood the working of both the circuits, slippers and clampers, how they are acting as slippers and why we are getting this clamped output?
Ma'am, like uh, in the clipper circuit, some part is clipped because the diode conducts in one direction. So
Hmm.
in for some part, like it is conducting for which output is equal to the input voltage. Output voltage is equal to input voltage, and for other part it is not conducting. So in
What about clamper?
now in clamper, the output gets shifted uh,
Hmm.
from the
Why?
and the reason I'm not remembering right now.
I have just told in this uh, today only, right? It
Yes,
is due to the charging of the capacitor. In one half cycle, the capacitor gets charged, and during the other half cycle, when our diode is in off state or when the diode is not conducting, at that time we are
yes,
getting the voltage of capacitor added up with the input voltage. So that is why we are getting the double of that at
input.
the output the voltage. Yeah, the voltage is the twice of the input voltage. Okay, so that is why our waveform gets shifted upward.
Yes, ma'am.
Okay,
Yes, ma'am.
upward or downward, whatever type of clamper we are using. Okay, schema trigger. So what is the main application of schema trigger, Ashish? Where do we use the circuit? Am I audible, Ashish? Ashish, am I audible to you? Hello? Hello? Hello?
Hello,
Ashish?
hello, ma'am.
Yeah,
Yes, ma'am.
I was asking the application of this schema trigger.
Ma'am, ma'am, like to analog to digital conversion. Like input, we are giving the sinusoidal wave, and output, we are getting the pulse.
Okay, that may be an application. Another,
Ma'am, ma'am, another I don't know.
the main application is the reduction of noise, or we also use them as level shifters. Then we also use them as the wave shaping circuits because wave shaping in the sense the if there is some distortion in the pulse, then we can reshape those pulse by using this kind of circuit. Okay.
Yes, ma'am.
Okay, fine, Ashish. Please tell me your roll number. I can't find your name in the list.
Ma'am, 10085.
85. Okay. You have shown me first three experiments.
Yes, ma'am.
Fourth, fifth, and sixth you have shown me now.
Yes, ma'am.
Okay, next is Ankush.
Yes, ma'am. Good morning, ma'am.
Morning.
May I present the screen?
Yes, please.
So is my screen visible, ma'am?
Yes, it is.
Yeah, so this is ma'am schema trigger, and basically we use it as you said for removing noise from signals used
Hmm.
in digital circuits, or
Hmm.
these are also used basically it is a comparator circuit, and we use it
Hmm.
with hysteresis implementation by applying positive feedback, right?
Hmm. Yes.
So in this experiment, ma'am, when the we are providing an AC input, if we let it as V2, so basically when
Hmm.
V2 is greater than Q3, the threshold voltage, Okay, so the Q3 is conducting and Q4 gives the output as high output, and we get the graph accordingly. So we get the higher threshold point when the Q3 the V1 is greater than threshold, and Q4 does not work because the feedback, due to the feedback circuit connected with Q4. Okay. Now we get the lower threshold point when the threshold voltage is V2. V2 will be lesser than the threshold voltage, and in that case Q4 will be conducting, and it will give the lower threshold voltage, and it will be the LTP for that. Now the graph would be something like this.
Fine. So here you're taking the output from the Q2, collector
Yeah.
of Q2.
Yeah.
Okay. 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 Fine. Okay. Good. Very good. So what is your roll number?
My roll number is 10026.
Okay. You have not shown me experiment number 5.
I have shown 4, 5, both I have shown.
Schemic trigger and excuse me, ma'am. And here we get two trigger point. This is high trigger point where Q3 is in conducting mode and Q4 is not conducting. And at this point we get low trigger point in which Q4 is in conducting mode and Q3 is not conducting.
Okay. Okay, Ronak, what is your roll number?
I'm 10278.